In this lesson, you're going to learn about equilibrium calculations. There are two types of equilibrium calculations that are common. The first type is one where you're given equilibrium concentrations and you use that information in order to determine an equilibrium constant. The second type of problem is one where you are given the equilibrium constant and you're going to determine equilibrium concentrations. In order to organize the data in this type of problem, we're going to use something called an ICE diagram or an ICE chart. ICE stands for initial, change, and equilibrium. A few little points about the ICE diagrams. When we're dealing with the equilibrium row, these concentrations are the only values that can go into the equilibrium law. So when you're setting up an equilibrium law, K is equal to, you must only enter equilibrium concentrations into that law. A second point about ICE diagrams is that all the values in the ICE chart are in moles per liter. So if you need to do any preliminary concentrations, for example, you're given the moles and the volume, you'll do those before entering any data into your ICE chart. You'll also see that you'll be able to enter pressures into this chart, usually in atmospheres. You're going to learn about the changes and how they follow the ratio consistent with the stoichiometry of the balanced chemical equation. So therefore, it will reflect the coefficients from the balanced chemical equation. You're also going to see that in the change row, you're going to show signs of plus and minus as a gain or a loss or an increase or decrease of concentration, depending on whether or not the substance has been produced or has been used up. Okay? And the reactants and the products will always be opposite, because as one side goes up, the other side goes down, somewhat like for a visual, like a teeter-totter. Let's look at the first kind of problem. The first kind of problem is one where we're going to use information given to determine the equilibrium constant K for a particular reaction. In this example, it says, suppose there are 2 moles of HI in a 1 liter flask at 425 degrees Celsius that react to produce H2 and I2. When equilibrium is reached, the concentrations of H2 and I2 are determined to be 0.214 moles per liter. Calculate the Kc for this reaction. Anytime you want to start a problem, you need to have the balanced chemical equation. So in this case, we're starting with HI and it's going to be in equilibrium with I2 and H2. And when we balance this equation, we see that we're going to need a coefficient of 2 in front of the HI. So this is our balanced chemical equation. Now let's create an ICE chart. The rows of the ICE chart, ICE, stand for initial, change, and equilibrium. So let's start by adding to the initial row the information that we're given. We know that 2 moles of HI were added to this empty flask. So the initial concentration of HI is 2 moles per liter. Therefore, I can enter 2 for the initial row of HI. There is no mention of any I2 or H2 in the flask initially. Therefore, the initial concentrations of these two substances is both 0. Now it's important to think of the initial concentrations as being the concentrations in the empty flask before any reaction has taken place. Let's look at what else we're given here. In this problem, it tells us that the equilibrium concentrations of H2 and I2 are both 0.214. Therefore, in the equilibrium row, under the I2 and the H2, we can record 0.214. Now you'll notice that I didn't put any units with the values as I entered them into this chart. This is because, as I said earlier, the only types of values that will enter into this chart are ones that are in concentration. So we know that if it's in the chart, the units are moles per liter. Another thing of note is that I'm paying attention to the significant digits, and I record the numbers with the appropriate numbers of significant digits. Now, for the change in an ice chart, we're always going to put the changes with respect to x. And we're always going to have the changes reflecting the stoichiometry of the balanced chemical equation. When we look at this reaction, we can see that the I2 and the H2 have both increased. Anything that starts with a value of 0 has only one way to go. It's going to increase. So the I2 and the H2 have increased their concentrations, and in turn the HI will decrease their concentration. Like I said before, for the reactants and products, they're going to have opposite signs. In this case, the products are increasing while the reactants are decreasing. Now I said that we'd like to put it in terms of x, reflective of the stoichiometry. So the change for I2, because it has a coefficient of 1, is going to be x. So it's going to increase by a value of x, while the H2, having a coefficient of 1, is going to increase by the same, x as well. For the HI, because there's a coefficient of 2, when we examine the stoichiometry, it's going to go down by twice as much as the I2 and the H2, which is represented by 2x. So it'll decrease by 2x. Now at equilibrium, the concentration of HI, if we look at the values above, we start with an initial concentration of 2 and we go down by 2x. For the I2 and the H2, we know the values, they are 0.214. Now what you can see here is that the I2 started at 0 and it increased by x, having a concentration at equilibrium of 0.214. From this, we can see that x is actually equal to 0.214. Because we know what x is, we can also solve for the equilibrium concentration of HI, which is going to be 2 minus 2 times 0.214. And that has a value of 1.572. At this stage, we know the concentrations of all of the substances at equilibrium. So to review, we were given information about one of the substances, and we used that information to find out what X was, and use that to in turn determine the equilibrium concentrations of all the substances. The question is asking us to determine the equilibrium constant Kc for this reaction. So what we need to do is we need to plug into the equilibrium law in order to find the equilibrium constant. So Kc is equal to the concentration of I2 times the concentration of H2 divided by the concentration of HI squared. So when we're writing our equilibrium law, we need to be very careful, products over reactants, and raise everything to the appropriate coefficients. I can now plug in the values that I have from the ice chart. So the concentration of I2 is 0.214. The concentration of H2 is 0.214. And the concentration of HI is 1.572. And I'll end up squaring that. When this is solved by simply plugging it into the calculator, you see that you get 0.019. Okay? And that is the equilibrium constant for the reaction given at 425 degrees Celsius. So that was type 1 of the equilibrium concentration calculations. Now we're going to look at type 2, where this time we're given the equilibrium constant and we need to use that information in order to determine some concentrations at equilibrium. Now you'll notice that this goes over 3 pages. The 3 pages are similar, and the 3 problems that we're going to do are similar in how we set them up. The difference is going to be the approach that we use in solving the problems. There are some shortcuts that we'll be able to take. Okay, the first one you'll see is called taking the square root, and we'll see momentarily what that actually means. In this problem, the equilibrium constant is given for the reaction to be 2.51 times 10 to the 4 at a certain temperature. The initial concentrations of H2 and Cl2 are 0.250 moles per liter. Determine the equilibrium concentrations for the reactants and the products. The equilibrium reaction is given below, and we're given the equilibrium concentration. We want to know what the concentrations of all of the substances are at equilibrium. So what we're going to do is, to organize our data, we're going to set up an ice chart. In this case, the initial concentrations of both the H2 and the Cl2 are given to be 0.250. There is no information about the HCl, so we know that the concentration of the HCl must be 0. In this type of a problem, there is no information about the equilibrium concentrations given in the questions. That's what we're trying to determine. The change row will follow the same process as before. We'll put the changes in terms of x. So in this problem, we can see that the HCl having 0 initial concentration, we know that that must increase. So we know that there is a positive value on that side in the ice chart. The H2 and the Cl2 in turn, being on the other side, being reactants, must decrease as this system approaches equilibrium. We'll put them in terms of x. So for H2 and Cl2, it's simply 1x, reflective of the coefficients. And for HCl, it's going to be plus 2x. Now what we can do is record these equilibrium concentrations in terms of x. So H2 is going to have a concentration at equilibrium of 0.25 minus some value of x, which is the same for the concentration of the Cl2. The concentration of the HCl at equilibrium is going to be equal to 2x. So in this case, if our goal is to determine what the actual equilibrium concentrations are, we need to use an approach where we're going to be able to solve for x. To solve for x, what we're going to do in all cases is sub into the equilibrium law. So if I look at my equilibrium law for this reaction, K is equal to the concentration of HCl squared over the concentration of H2 times the concentration of Cl2. I know the value of the equilibrium constant for this problem. It's 2.51 times 10 to the 4. And I can plug the values in terms of x into the law. So the concentration of HCl is 2x. The law tells me that that's going to be all squared. In the denominator, I can see that I've got 0.25 minus x 2 times. So I'm just going to write that as 0.25 minus x all squared. Now this, in solving for x, could be a messy math problem, but we can simplify it by noticing that this is a perfect square. The heading of this problem was taking the square root for this reason. The right-hand side of this equation is a perfect square. We can take the square root of the numerator and the denominator. So what we're going to do to make the math a little bit quicker is we're going to take the square root of both sides of this equation. So I'm going to take the square root of the equilibrium constant, and I'm also going to take the square root of the right-hand side. This simplifies this equation to 158.43 is equal to 2x over 0.25 minus x. To solve for x, I need to bring this entire expression, 0.25 minus x, to the other side by multiplying. And after some expanding and simplifying, you're going to find that x is equal to 0.247. Now that we know the x value, we can answer the question that was posed, which was determine the equilibrium concentrations for the reactants and the products. We have in our ice chart the equilibrium concentrations in terms of x. So what we need to do is simply sub in the value of x in each of these cases to determine the equilibrium concentrations. So the concentration of H2 is equal to the concentration of Cl2, which is equal to 0.25 minus x, which gives us 0.003 mole per liter. In terms of significant digits in this case, because we're doing a subtraction, we're going to pay attention to the decimal places for our final computation of 0.003 mole per liter. I used 3 significant digits to determine the 0.247 because that involved multiplication and division. And for the final answer, because it is arrived at through a subtraction, I need to use the decimal places. For the concentration of HCl, we see from the ice chart that is equal to 2x, and therefore when we multiply 0.247 by 2, we get 0.447. moles per liter. The square brackets do mean concentration, but that doesn't remove your obligation to report the units of moles per liter or molar represented by a capital M. I encourage you to pause the video for a moment and develop an ice chart for this next problem. And once you've done that, you can start the video again, check that you've created the correct ice chart, and then we'll discuss the solution for this one. Okay. In this case, we're working with partial pressures. It gives us the equilibrium constant Kp to be 85. It gives us the partial pressure of SO2 to be 1 and the partial pressure of NO2 to be 0. There is no mention of the NO or the SO3 in the system, so their initial concentrations, partial pressures, are 0. To complete the change row, we can see that the products are going to increase. So therefore we know the reactants are going to decrease. They all have a coefficient of 1, so it's simply for SO2 it's minus X. For NO2 it's minus X. And both the products, NO and SO3, increase by some value of X. Our goal here is to determine the equilibrium partial pressures. So to do that, we need to determine the value of X. So at this stage, it looks like exactly the same problem as we were doing before. We've got our ice chart completed, values of equilibrium in terms of X, and we need to solve for X so that we can identify the equilibrium pressures. When we look at the equilibrium law for this, you'll see that it's X squared over 1 minus X times 2 minus X, and that's all equal to 85. In the previous example, at this stage, we were able to take the square root of both sides of the equation. But unfortunately, in this particular example, it is not a perfect square. Okay? This expression is not a perfect square, and therefore we cannot simply take the square root to clear the x squared terms. In order to solve this, this will be the longest type of problem. We actually need to expand and simplify and set it up so that we can actually use the quadratic formula to determine what x is. That will require moving the 1 minus x and 2 minus x over to the other side, expanding, and bringing everything over to one side, because to use the quadratic formula, we want the equation in the form ax squared plus bx plus c is equal to 0. So take a few minutes and do that expansion, okay, and make sure that you're comfortable with doing that math. What you should arrive at is 84x squared minus 255x plus 170 is equal to 0. We've got it in the right format to use the quadratic formula. So a reminder, I'll put over here the quadratic formula so that x is equal to minus b plus or minus b squared minus 4AC all over 2A. When you sub into the quadratic formula, you'll get two roots. So in this case, x is equal to 0.987 or 2.04. These are the two values for x that you'll determine when you sub into the quadratic formula. And you're going to want to make sure, obviously, that you can do this before moving on. Once we get to this point where we've got two values for x, we need to determine which one is the valid root. So if we look back to our data at the beginning, we can see that for the NO and the SO3, they're simply equal to x. They're partial pressures. So any value will do for them. For the SO2 and the NO2, however, they are limited because they have values of 1 minus x and 2 minus x. From this information, we can see that x can't be any bigger than 1. If x was larger than 1, the pressure of SO2 at equilibrium would be less than 1, which doesn't make sense. Okay, we need to have positive values for our pressures or concentrations. So what this means is that since x must be less than 1, okay, therefore the 2.04 is not valid. The original question asks you to find the partial pressures of each of the substances at equilibrium, which we are now prepared to answer because we know that x is equal to 0.987. So the partial pressure of SO2 is 1 minus 0.987, which is equal to 0.013 atmospheres. We know that the partial pressure of NO2 is equal to 2 minus x, or 0.987, and is therefore equal to 1.013 atmospheres. And finally, the partial pressure of NO is equal to the partial pressure of SO3, and they're simply equal to x, therefore they're equal to 0.987 atmospheres. Okay, all recorded to 3 significant digits, reflective of the question. Again, I'd recommend that you pause the video, read the next problem, and set up an ice chart that you feel would be appropriate for solving the problem. This falls under the same category. You're going to be given the equilibrium constant, and you're asked for information about a substance at equilibrium. And you'll see there's a different title, okay, which we'll discuss once you've got the ice chart set up and we're ready to solve. This equilibrium describes the dissociation of I2 molecules into 2I. It gives us the initial concentration of the I2 as 0.200. The I has an initial concentration of 0. The changes with respect to x, the 2I must increase by some value 2x, and the I2 is going to decrease by x, reflective of the stoichiometry of the balanced chemical equation. So as you can see, the ice chart looks very similar. The problem-solving approach is very similar to the previous ones. We need to know what x is in order to answer the question. To solve for x, we always sub into the equilibrium law, which in this case is I squared. So we've got 2x all squared divided by I2. And that's equal to 3.8 times 10 to the negative 5. So at this stage, it looks similar to the last problem. This is not a perfect square, so we're not able to take the square root of both sides. So really, it looks like we might need to use the quadratic formula again. But as you can see from the title, we are going to be using an approximation. Using an approximation is going to be possible when you have a Kc that is very small. Our definition of very small at the moment is anything of the order of 10 to the minus 5 or smaller. So 10 to the minus 5, 10 to the minus 6, anything that is small. Now you remember from our discussion of magnitude of Kc, when we've got an equilibrium constant that's very small, what that's going to mean is that the amount of reactants in the system at equilibrium are going to be much higher than the amount of products as a relative value. What that means is, if we look at this reaction, it's really not going to go very far to the right. So the amount of products that we produce is going to be very small. And what that means is that the amount of I2 that actually gets used in this reaction is going to be very small. Now what we're going to do, or the approximation we're going to make, is that at equilibrium, the amount of I2 that we have is virtually 0.200. Now we need to be very careful. We're not making the assumption that x is 0. We are making the assumption that the change is going to be so small that when we actually do this computation, 0.2 minus x, we're virtually going to get the same as the initial concentration, which in this case is 0.2. So if you try that on your calculator, if you take a value of x, something like 0.000001, a very small value of x, you'll see that really, when you round that final answer, it's approximately equal to 0.2. By making this assumption, we're omitting the x term, and so what we're going to have to solve is 4x squared over 0.2 is equal to 3.8 times 10 to the negative 5. So by making the approximation, we've gotten rid of the x term, so we don't need to use the quadratic anymore. This is much easier to solve, and we are left with x is equal to 0.00138. The question asks us for the concentration of I at equilibrium, which is equal to 2 times x. So this is equal to 2 times 0.00138. Now you might be saying to yourself, well, if the amount that the I2 decreases by is insignificant, why is this amount insignificant? Well, it may be. This amount of substance that we're putting into the system may be significant. Okay? In our world, I2 isn't as harmful as I atoms are. So if this reaction is taking place, we want to know how much I we're putting into the atmosphere, because it could potentially be toxic. In order to determine if your approximation is valid, what we can do is we can actually check to see if the change is less than 5%. So you're going to take your change, which is your x value, You're going to divide by the initial. Okay, so in this case, your change is 0.00138. Your initial concentration was 0.2, and you're going to multiply that by 100. And what you're going to see is that that is far less than 5%, okay, which makes it okay for us to have made this assumption. At this stage, you can complete these practice exercises and the online equilibrium assignment number 3.